You're watching this video and you don't even realize that right now, billions of particles from space are passing through you. They fly through your body, through the Earth, and almost never interact. But what would happen if even one of them hit? And could this happen right now? There have been cases in history that sound like science fiction. But is it reality?
Neutron stars are the densest structured objects in the universe, except for black holes. In their cores, it is believed one can find the most dangerous substance in the history of the universe, strange matter. And this substance is strange not just because of its name. Strange matter breaks the laws of the universe and is even capable of destroying everything that comes into contact with it. What a nightmare, you might say, but it's not all that bad. This amazing matter, among other things, is capable of revealing a lot about the history of the universe, about its very earliest stages. To understand just how incredible this strange matter seems, we first need to grasp a few basic facts about it. So, what is a neutron star, and how does strange matter break the laws of the universe? A neutron star is the remnant of a giant supernova explosion. The core of the star collapses under its own increasing gravity with such force that it compresses all the particles inside itself. Electrons collide with protons and turn into neutrons. All the emptiness inside atoms is suddenly filled with particles that aren't particularly happy about each other's company. But they have no choice. They desperately push in the opposite direction. They push back against gravity, resisting collapse with all their might. If gravity wins, then meet the new black star. If the particles win, a neutron star appears. Because of this, neutron stars resemble giant atomic nuclei the size of a city, but with the mass of our sun. Imagine that a single spoonful of neutron matter on Earth would weigh more than all the matter that makes up the moon. This is where things start to get strange. The conditions in the core of a neutron star are so unusual that the laws of nuclear physics change drastically there. These conditions can lead to the emergence of a strange and dangerous substance. But let's not get ahead of ourselves. First, we need to remind ourselves of the laws themselves before figuring out how to break them. Protons and neutrons are particles that make up the atomic nucleus. They are composed of even smaller particles called quarks. Quarks don't like being alone. You can try to separate them, but the harder you pull, the stronger they attract each other. If you use a lot of energy to separate them, they'll just steal it and use it to create new quarks. Quarks exist only as building blocks for other particles and have never been considered on their own. They have funny names: up, down, strange, charm, beauty, and truth. But only two of them are capable of creating stable matter, up and down quarks. All the other variations decay quickly. But this rule may not work inside neutron stars. The forces at work in the cores of these stars are so extreme that they resemble the processes that took place in the universe right after the Big Bang. So, understanding the rules by which quarks exist inside neutron stars is a way to dive into the history of the universe and an opportunity to better understand its ancient nature. According to one theory, inside a neutron star's core, protons and neutrons break down, turning into a mass of quarks. A colossal number of particles turn into a single object made entirely of quarks. This kind of matter is called quark matter. A star made of it is called a quark star. The idea of quark stars was developed in a 1970 note by Toshiaki Ito, and in 1971, Arnold Badmer showed the possibility of the existence of strange quark matter, composed of three types of quarks. This idea gained particular popularity after the publication of Edward Witten's 1984 article about quark nuggets, clumps of invisible quark matter. According to Witten, such nuggets, also called strangelets, could have remained in the universe after the Big Bang and formed dark matter. And by coming together under the influence of gravity, they could have formed quark stars. From the outside, such stars may be almost indistinguishable from an ordinary neutron star. Now we can talk about that very dangerous substance. If the pressure inside a quark star becomes high enough, strange things start to happen. In the cores of neutron stars, some quarks turn into strange versions of themselves. They are much heavier and stronger than their ordinary counterparts. Their mass is what makes up strange matter. It is this, according to many scientists, that could be an example of a perfect substance. Perfect density, absolute stability, and indestructibility. This matter is so stable that it can exist outside of a star. And that's a problem. The ideal is contagious, so any other matter that comes into contact with strange matter will try to match it, turning into strange matter. Protons and proton neutrons, which make up both you and me, will start to decay, joining the mass of strange quarks. The only way to escape this disaster would be to throw this matter into a black hole. It might seem like there's nothing to worry about if all these quarks are inside a neutron star, but what happens if one such star collides with another? Before collapsing, they will eject an incredible amount of their contents, including tiny particles of this very strange matter, which are commonly called strangelets, meaning a strange droplet. These particles are capable of traveling enormous distances until they encounter a random star or planet. After the collision, the particle will instantly begin to turn everything around it into itself. The collision of a strangelet with the nucleus of an atom can cause it to turn into strange matter, which is accompanied by the release of energy. As a result, new strangelets fly off in all directions, which could theoretically lead to a chain reaction. By the way, the best advertisement for strangelets was made by the Large Hadron Collider, the pride of humanity and at the same time an accelerator, a charged particle accelerator. Let me remind you that this accelerator was put into operation in 2008 with the participation of scientists from more than 100 countries, including Russia. Such a grand project could not help but attract the attention of those who are convinced that the experiments taking place there could even threaten the very existence of life on Earth. Supporters of the worst-case scenario have long believed that the killer Strangelet would be born there, not come from outer space. One immediately recalls the immortal novel by the American writer Kurt Vonnegut, Cat's Cradle, where all the water on Earth turns into Ice 9 under the influence of a fictional substance. Fortunately for us and unfortunately for the pessimists, the results of many years of experiments show that no stable strangelets are formed as a result of the collider's operation. But let's get back to the cosmic visitor. Imagine that instead of a random planet in the path of a strangelet, it's Earth that's in its way. Its mass would catastrophically decrease, and everything living and non-living on it would merge into one huge mass of strange matter. If a strange particle collides with our sun, its size won't decrease much, but its brightness will drastically drop. The Earth would simply freeze. Thus, at the current level of technological progress, humanity simply has no way to predict, let alone prevent, a possible catastrophe. A terrifying prospect. But there is another theory, according to which strange matter particles are a common occurrence in the universe. They don't cause harm, but instead helped expand the universe in its early days. It is possible that strange matter is the very force that holds entire galaxies together. Jinjin Yongjin and his colleagues from Nanking University believe they have discovered strange planets made up of hypothetical strange quarks.
Странной материи.
Their paper has been accepted for publication in the Astrophysical Journal. On average, the planets we know have a density of about 30 grams per cubic centimeter, but those made of strange matter should be 1 trillion times denser. Such incredible density allows them to persist even when they are extremely close to a similar strange star, and to orbit just a few dozen kilometers from its surface without being torn apart, withstanding the immense power of tidal forces. planet Earth is rightfully called the perfect location for human life. If we rise even a little above its surface or briefly leave the hospitable embrace of our own celestial body, the laws and theories start throwing out all sorts of surprises, not always pleasant and sometimes completely incomprehensible. This becomes especially noticeable if you accelerate an object to unimaginable speeds. Take, for example, the general and special theory of relativity, a royal gift to the world from Albert Einstein. A number of paradoxes are associated with it, which are extremely difficult to grasp, because the conclusions drawn from experiments contradict the ideas accepted in classical physics and completely shatter the castles of intuition. At the same time, in essence, they are absolutely correct and natural. Albert Einstein is perhaps the most famous physicist and theorist on the planet. He is credited not only with the special and general theories of relativity, but also with the quantum theory of the photoelectric effect and heat capacity. He was the first to describe the exotic state of matter known as the Bose-Einstein condensate, and he publicly announced the phenomenon of Brownian motion. Thanks to Einstein, we seriously consider quantum teleportation and other effects that are difficult to reproduce, even with our current level of technological development. What can we say about the era when the German genius was creating? Truly, this man was born ahead of his time. But enough with the introductions. Let's take a closer look at the two most popular paradoxes brought to life by the special and general theories of relativity. The first of them is the twin paradox. Unfortunately, at this stage, the experiment can only be conducted as a thought experiment. The essence of it is that one of the twins is an astronaut who travels into deep space at a speed that is currently impossible in practice, more than 90% of the speed of light. All this time, the second brother remains on the surface of the Earth. The question is, which of the twins will be younger by the time the traveler returns to his home planet? Or will their ages remain the same? This paradox involves the postulates of the special theory of relativity, which states that from the point of view of a stationary observer, processes in moving objects slow down, but at the same time, the equality of inertial reference frames is not canceled. The contradiction is actually built on this very statement. Logically, if you look from the point of view of the twin who stayed at home, the astronaut's time should be slowed down, so his clock will inevitably lag behind. On the other hand, the traveler, looking at the situation from his own perspective, or rather from his space shuttle, realizes that the Earth is also not standing still, but is moving along with the stay-at-home twin's clock. This means that the brother who stayed on the planet should be the one whose clock lags behind. But from the point of view of a third outside observer, the relatives are absolutely equal, meaning the clocks will show the same time for both of them. So who is right? It turns out that the special theory of relativity is correct, which says that if we don't take Earth's gravity into account, it's the traveler's clock that will lag behind. Let's take a closer look at the issue. For example, Twin A sets off for star X, which is 20 light years away. The shuttle's speed is 0.9 times the speed of light. Under these conditions, the astronaut will reach the star in just over 22 years, according to his own clock. After that, the ship will turn around and head back. As soon as the shuttle lands, the youthful and fit twin brother will be met by an old man who has waited for his relative for more than a century. But why not 44 years? There is no paradox yet. It's just that when moving close to the speed of light, the effect of time dilation comes into play. The faster you move, the slower your clock runs. That's why, from the perspective of an Earth observer, 103 years have already passed. After all, time for the astronaut has slowed down significantly, and according to the formula, 44 years can be multiplied by a factor of about 2.3. And now remember what we talked about at the beginning. That's right, about different points of view. And the astronaut's perspective changes as well. From his point of view, as we already mentioned, his stay-at-home brother is not stationary at all, since the planet is constantly moving. So it should have been the astronaut who aged, not the other way around. How do we resolve this stalemate? Actually, it's not that complicated. You need to start from the world lines of the twins. They are completely different. If the home body is at rest relative to one inertial frame, the astronaut is not just moving at a constant speed. He periodically experiences the effects of acceleration. For example, when decelerating near a star and turning back. It is the differences in physical conditions that resolve the apparent paradox. Thus, an exact calculation demonstrates an obvious fact. The twin who remains stationary relative to the planet will be older, since he did not experience any acceleration or other effects during this time. To support this proof, it should be added that in modern accelerators, particles moving at near-light speeds live much longer than those at rest. In addition, there are numerous experiments comparing the readings of clocks on airplanes and on the Earth's surface, which demonstrate slight but still noticeable differences in the data. In short, this paradox has been resolved. Let's move on. Now we've come to Lorentz length contraction, which gives rise to even more astonishing oddities. One of them is called, as if it were a fable by Krylov, the rod and the hanger. Imagine that you are standing and watching as a metal rod, 10 meters long, flies past you at a very high speed. There is a hanger ahead that is 6 meters long. Attention, here's the question. Is it possible for circumstances to be such that the rod can be completely hidden inside the hanger? It's worth remembering here that the theory is not called relativity for nothing. In this case, the law stating that simultaneity is relative applies. What does this mean in practice? Once again, let's turn to the separate observers. A stationary person inside the hanger will, at some point, definitely see the rod flying by, completely occupying the space. From the point of view of the observer riding the rod, it is the rod that is stationary, and the hanger is rushing toward him at tremendous speed. Does this mean it's complete nonsense? Was Einstein really insane and not a genius? Oh no, although often genius and madness go hand in hand. But that's not the point right now. When we talk about the length of an object, it means that we receive a signal from both of its ends at the same time. And yes, if the observer is inside the hanger, these events really do happen simultaneously in his frame of reference. But this perception is not the same for the one who is riding on the rod. In his frame of reference, first one end of the object aligns with the right door of the hanger, and then after some time, the same thing happens with the left end of the barn, or the other way around. It's important to understand that these events will never be simultaneous from the rider's point of view. In short, to put it simply, too much in the theory of relativity is based precisely on the observer's point of view, and the final conclusions depend on that. You might be outraged. Why are we busy describing the lives of twins and hangers when real life is passing us by with all these abstruse theories? This is where you're mistaken. There are plenty of examples where general and special relativity really change people's worldview. For example, a person sees gold as honey yellow precisely because of effects caused by the theory of relativity, since the atoms of the metal, due to the enormous speeds of the electrons, begin to strongly absorb blue light. The result, your pendant looks gorgeously golden. Even Mercury is liquid precisely because of the change in the diameter of electron orbits, which is caused by the theory of relativity. Atoms simply can't form stable bonds. The result, increased fluidity of the metal. And the last vivid example is electricity and satellite navigation systems. GPS systems must take relativistic errors into account. Otherwise, plane crashes and geolocation failures would be a routine part of our daily lives. As for electricity, the main principle behind transformers is a relativistic effect called magnetism. So you shouldn't think that the theory of relativity doesn't affect us at all. Without its effects, human life wouldn't be the way it is now. Orthodox astronomy is used to considering the most powerful cataclysm to be the explosion of supernovae. But already in the 1960s, some scientists held a different opinion. It would seem that a giant collapse and the instant ejection of matter from a massive star into space is quite an epic event, with which few things in the universe can compare. But still, we will take the liberty of disproving the generally accepted fact. Back in 1963, scientists Sandage and Linda from the USA published incredible observation results of the galaxy NGC 3034, also known as the Cigar. The Cigar. At first, this galaxy, located in the constellation Ursa Major, attracted astronomers with its unusual color. Instead of having a bluish tint, as is typical for respectable galaxies of the second group, the Cigar shone brightly with an orange color. Further research showed that active processes are taking place in the core of the galaxy, and a bilateral outflow of diffuse matter extends to simply unimaginable distances, up to 3 kiloparsecs in each direction. To grasp the enormity of this figure, it's worth remembering that a parsec is about 30 trillion kilometers. Obviously, 1 kiloparsec contains 1,000 parsecs. Based on this data, scientists drew an even more unusual conclusion. In order to travel 3 kiloparsecs, the gas must be rushing from the core of Sagara at a speed of 1,000 kilometers per second, and the explosion of the galactic center itself is believed to have occurred 1.5 million years ago. The total mass of matter released during the colossal explosion, according to astronomers' estimates, is 5.6 million solar masses, and the total energy of the explosion amounted to an octillion joules, 9 times 10 to the 48th. That is, the energy of the explosion of the core of the galaxy with the trivial name Sagara is 1 million times greater than the impressive burst of a supernova. Returning to the question of the most spectacular catastrophes in the universe, the explosion of a galaxy's core definitely takes first place, since it's hard to imagine anything more grandiose. But maybe this is a one-time event, an unplanned accident by the universe? Using the example of Sagara, which was affected by the cataclysm, scientists decided to prove to humanity that the explosions of galactic nuclei have happened, are happening, and will continue to happen as long as the universe exists. If we take as a basis the assumption that the explosion happened 1.5 million years ago, and during this time the matter has moved 3 kiloparsecs away from the core of Sagara. So by calculation, we can determine that in another 10 million years, it will be about 15 kiloparsecs away from the galaxy NGC 3034. During this time, the gas will lose speed and energy. So in 10 million years, there will be almost no traces left of the hellish event. Therefore, if we assume that the unknown world of galactic communities has existed for 10 billion years, and each of the galaxies periodically explodes, then only in 1 out of 1,000 star families can a flare be observed. Therefore, it is not surprising that only after 40 years of observing the life of galaxies did scientists discover such an astonishing event. Now, astronomers are focusing their attention on the galaxies NGC 5195 and NGC 3077, which have features similar to the Cigar galaxy. The only difference is the absence of radio emission, which always accompanies an explosion. But perhaps the cores of these galaxies flared up earlier, so the diffuse matter coming out on both sides is still visible, but the traces of radiation are no longer there. These distant star families also caught the attention of the famous Soviet astronomer Boris Vorontsov-Velyaminov. The scientific community took a closer look at the galaxies of the second group, which includes the Cigar, and discovered several more clusters with the same anomalous orange-red luminosity, about 10 times higher than normal. Of course, people on Earth are more interested in the question of their continued relatively peaceful existence. What if such an explosion happens in the core of our cozy galaxy? Is there a real threat to Earth? In the 1980s, the hypothesis that galactic magnetic fields would prevent particles from traveling vast distances was disproved. On the contrary, the rays will cross them with virtually no obstacles. It turned out that after an explosion in the core of our galaxy, super waves can arise, traveling at nearly the speed of light, which will inevitably reach the boundaries of the solar system. It is assumed that a similar massive outburst already took place during the Ice Age, when the center of the Milky Way was in an active phase and caused global climate changes on the planet. Do you want more episodes like this? Then hit like and write the hashtag #UsedYou watching Hubble, and surely the law of the universe will reward you.